Good afternoon, everyone. Thank you very much for coming along to this webinar this afternoon. So we're the UK CCSRC, and the webinar, obviously, as you can see, is on CCS Putting the Net in Net Zero. And this is part of the EPSRC's Engineering Net Zero Week. So I'm going to hand straight over to John Gibbins, our director, who will be running the session. Thank you.
Okay, thanks very much, Mel. So if you've got any comments or questions, please use the chat. We'll perhaps have some time to pick them up afterwards. I'm going to go straight through the talk. I'm the director of the UK CCSRC and also a professor at University of Sheffield. And we'll also be hearing from Stuart Haszeldine, who's the deputy director for storage of the UK CCSRC and professor of CCS at the University of Edinburgh. So, what's the problem? Well, the Earth's got a lot of carbon. Most of it is in the continental crusts, but in the bit we live in, there's carbon in soils and vegetation, permafrost, bit in the forests, and then there's a certain amount of carbon in the atmosphere. This is the pre-industrial atmosphere. There's carbon dissolved in the surface layers of the ocean, which doesn't mix very quickly with a deep and intermediate ocean. The turnover time is about 10,000 years. And now there's more carbon than there was. There's fossil carbon that's been added. There's some land use carbon that's been added to the atmosphere that was in this surface layer. And there's also the possibility of reserves of fossil fuels, further carbon, going into the atmosphere and the surface layers of the ocean. And these are reserves, known, proven extractable carbon. The available resources are much higher. We could actually find a lot more fossil carbon in the Earth's crust. There's also a certain amount of carbon that's come from carbonate rocks when we were making cement. So the problem is, really, what do we do about this? And in terms of global warming, nearly 10 years ago, it was fairly clear that the problem was cumulative emissions of CO2. So we plot temperature rise against cumulative anthropogenic CO2 emissions. This is as gigatons of carbon, not carbon dioxide. And you can see that if you get up to about 1,000 gigatons, 1 teraton of carbon, you're getting up to 2 degrees. So the thought on that was, again, at this period from Miles Allen at the University of Oxford, was, well, okay, so we've got a certain amount of carbon to emit. In 2009, we had used about half that budget. We wanted to stop emitting to atmosphere by the time we got to 1,000 gigatons of carbon. And he said, well, actually, we're not at the moment capturing and storing any of the carbon we use, but we should increase the fraction of the carbon we use, fossil carbon we use, that we capture and store back underground securely until we get to 100% by the time we've reached this limit that we can put in the atmosphere, as we then thought, for 2 degrees. And that's both a necessary and a sufficient way to avoid dangerous climate change. It doesn't say how long it takes you to get to that 1,000-ton budget. It doesn't say how much fossil carbon you're going to be using by the time you get there. But what you do know is that by the time you get to the limit, you need to be net zero. And net means that any fossil carbon that comes out of the ground goes back into the ground. That's basically it. So how do you do this, this netting? How do you take carbon, fossil carbon that's coming out of the ground, and put it back in? Well, you capture it. But you need to know where it's coming from. So this is historical emissions of carbon. This is millions of metric tons per year, but the area under the curve is the cumulative emissions. So this is coal, the bottom tranche. Next bit's oil. Then we've got natural gas. And then we've got cement, limestone. So it's not a fuel. but it's still emitting CO2 when we turn limestone into cement. And so you can see coal, we might be able to capture from a large stationary source. Most coal gets used in power plants or industry. Some natural gas and cement we might get from large stationary sources. But for the oil, that's all moving, it's transport. So if you want to capture from oil use, we're going to have to use air capture from the air. We'll talk more about that later. You can also see, actually just interesting on here, you know, coal gets often gets demonized as the source of the problem. Well, yes, but actually now we're using an awful lot of oil and gas. Just stopping coal is not going to sort out the problem or anywhere near. That was the position back in 2000, 2009, 2010, but further on, when we thought we could cope with 2 degrees and we wanted to limit total emissions to 1 teraton of carbon. Now, the IPCC special report on global warming of 1.5 degrees shows that most scenarios need to go to net zero by around 2050, but we'll still have put too much CO2 in the atmosphere. We'll have locked in warming unless we subsequently remove CO2 from the atmosphere and also from the surface layers of the ocean. There's an equilibrium. So as you take CO2 out of the atmosphere, it'll come essentially bubbling out of the ocean, or at least released. You won't see the bubbles, but it'll come out and you'll have to remove that as well. So basically you've got to pull the same tonnage out that you put in over and above the limit you can cope with to get 1.5 degrees of warming. So we've got to take CO2 out of the air to compensate, indirectly capture emissions from oil use. Eventually, we're also going to have to take CO2 out of the air to remove historic emissions. We're not there yet. We're nowhere near net zero. But even when we get to net zero, the day after, we've got to go net negative. This is just an even later assessment by the IPCC 2021. This is the current round of IPCC assessments. And you can see that the only scenarios that avoid serious warming go net negative in the second half of the century. So net zero, yeah, great, but net negative's coming. One of the things we've seen in CCS development is an emphasis on clusters. So we used to sort of think about simple CCS projects. You had a CO2 source, you maybe had a pipeline, you had an injection well, and we'll be looking more at that soon, how you inject it, but all grouped together and just acting in isolation. But now we're thinking much more about clusters where you bring together a pipeline, a transport infrastructure, like pipeline, shipping or rail. You bring in a selection of storage sites, which Stuart will tell you about soon, which could be in deep underground rock formations that will hold the CO2. And we bring in a range of CO2 sources and we put those together in sort of an ecosystem. And that cuts costs for everyone. It reduces risks. It's a very good idea. And we'll see a little bit more what we plan to do in the UK. We've got clusters developing here, Canada, Netherlands, US now are looking at clusters. A lot of places are looking at this infrastructure, which really enables CCS deployment. Very complicated slide here, which I'm not going to attempt to go through in detail. But what I will point out is there's a few common elements. This is the transport element, relatively limited number of options: pipeline, ship, rail, or road. Permanent storage options, geological storage, or in stable carbonates. That's locking it back in limestone essentially. But you can capture CO2 in an awful lot of ways from different sources using different technologies, and you can also capture it from the air, which again gives you CO2 to go to permanent storage. And there's also some indirect routes, the blue boxes, biomass, where you rely on growing plants to take CO2 from the air for you. And then instead of leaving them lying around to rot, basically, most biomass would disappear in the medium term, as Stuart will explain. You use it, burn it, essentially, get carbon dioxide, and then take that carbon dioxide away for permanent storage. So again, that gives you a permanent removal. The costs for doing this per ton of carbon dioxide stored are variable and also unknown, because by and large, we're not doing a lot of this yet. So they remain to be developed. But indicative costs are from maybe as low as $25 for really low cost sources where you're taking CO2 out of natural gas before you use it. Bulk are probably around somewhere between $100 and $150 per ton for capture from energy in power generation, making iron and steel, cement. And then direct air capture still being developed, even less developed than some of these other industrial applications, anywhere between maybe, I don't know, $150 and $400 quoted here. It's a credible range. So a range of different costs, but if you don't have any alternatives, still worth doing. I talked a lot about storage and permanence, even so far. We'll hear a lot more about it soon. The question that often gets asked is how much storage is available in the world. And this was a map looking at storage sites. The amber areas are areas where you've got good prospects for finding rocks that you can inject fluid CO2 into. So pretty widely spread in the world. What's not shown on here also is volcanic rocks that will also react with the CO2. And a lot of those areas that are shown as non-prospective also have some volcanic rocks that will react with CO2, and that area of permanent storage is being developed too, notably in Iceland. Okay, so that's given a quick introduction. Storage is absolutely the key to carbon capture and storage. So I'm going to pass on to my colleague who's prepared a recording interview. So we'll hear from Stuart Haszeldine, who, as I say, is Professor of CCS at University of Edinburgh, Deputy Director for Storage at the UK CCSRC, and also Director of Scottish CCS.
Hello, I'm Stuart Haszeldine from the University of Edinburgh, and I'm going to talk to you about how carbon dioxide is stored deep underground and how long it needs to be stored for. And so we'll have a look at some slides to help us understand that. And you can see we're talking about how long duration and how safe and secure CO2 storage is. Well, we've heard previously that we can capture carbon dioxide in many different types of facility, whether that's a power station or a petrochemical works or an oil refinery or a steel works. So we can take the fossil carbon from coal, gas or oil and put that through a combustion facility. We can do the same with biomass, whether it's wood from trees or straw from crops, or we can capture carbon dioxide from air. And we can put all of those different types of carbon dioxide deep underground into a CO2 storage reservoir site, a porous sandstone rock, which is anywhere between 1 and 4 kilometres deeply buried beneath the surface. And the carbon dioxide in that deeply buried sandstone reservoir lives in the pore spaces, resides in the pore spaces between and around the sand grains shown on this electron microscope, powerful image, powerfully magnified image. And so what we're looking at in real life is rocks like this sandstone rock here. You can see the rounded grains, and in between the grains, you can see small pore space. And underground, that pore space is filled with salty water. But what we're doing here is drilling into that rock and displacing the salty water with liquid carbon dioxide. And so on this scale model here we've got a power plant mining coal open cast at the surface, burning some coal, capturing carbon dioxide and sending the carbon dioxide through a pipe to these 2 boreholes here, which go deep, deep underground. long, thin borehole, maybe 1 kilometre, maybe 4 kilometres down, and those inject carbon dioxide into that porous and permeable rock layer. And on top of the rock layer is a seal, a geologically impermeable membrane layer, which is the mud rock, made of clay material, and that stops fluid flow going through it. And so here in the cross section, we see the sand grains in this rock greatly magnified. And in between the sand grains, the white is the liquid carbon dioxide, which has been injected and has pushed the dark blue salty water out of the way. And the carbon dioxide deep underground is stored in 4 different ways, which makes it really, really safe and secure to keep that carbon dioxide deep underground. Firstly is the stratigraphic trapping, which is trapping the buoyancy beneath this shale top seal, this impermeable membrane, so there's no flow through that membrane. Secondly, you can store carbon dioxide, becomes stored when it moves through the porous rock. It leaves behind small individual droplets of carbon dioxide, rather like a dampness of carbon dioxide in the porous rock. And those bubbles are so small that they cannot squeeze out through the connections between the pores. So the bubbles are trapped in those pores forever geologically. And we can also trap carbon dioxide by dissolving carbon dioxide into the liquid water, just the same as sparkling water you buy from a supermarket has carbon dioxide dissolved in it. Here, deep underground, we're dissolving the carbon dioxide in salty water. And when that carbon dioxide is dissolved in the salty water, it becomes more dense and sinks rather than floats. So again, it's securely stored forever. And the last mechanism here is over thousands and tens of thousands of years, some of the carbon dioxide can gradually change into growing new minerals, carbonate minerals, which have locked up the carbon dioxide then forever geologically. And the types of reservoir we're looking for are like this sandstone here from North America, where a sandstone may be 100 meters in thickness and a very flat, very simple bedding layering. You can see the horizontal beds going through these rock towers here. And that sandstone, very simple, extending for maybe 10 or 20 kilometers, so that we've got plenty of room in that microscopic pore space to inject the carbon dioxide. And to give us some idea of the size of these sandstone structures, which the sandstone locations where we're trying to inject carbon dioxide as permanent storage, here's a map of the oil field Miller in the North Sea. This is midway between Scotland, the Orkney Islands and Scotland, midway between that and Bergen from Norway over on this side of the map. And the Miller oil field is shown magnified here with this scale bar. And the Miller oil field then is this candidate storage site to take several tens, 30, 50 million tons of carbon dioxide. But enlarged and put to the same scale as the city of Edinburgh, we can see that the Miller oil field is about the same size as the city of Edinburgh. So this is quite a complicated thing to do, but that's what oil and gas companies are very well experienced in doing, this type of underground investigation and underground development, because they've been doing that very successfully to remove oil and gas from the underground since the early 1900s. And we can also borrow some technologies from the oil and gas organizations so they understand the street map of the sandstone which they're dealing with. Obviously, we can't determine all the detail of the street map, but they know between one borehole and the next borehole, maybe 500 meters apart, that between those two boreholes there is all sorts of fast flow complexity and sideways flow, small, narrow, thin flow across narrow streets. And the oil company job is to try and understand that flow well enough to develop and predict where that fluid goes and how that fluid will stay underground. But of course, once it's underground, we can safely and securely monitor that carbon dioxide using lots of technology and equipment from the oil and gas industry, where there are literally many tens of technology surveying type of techniques which can be utilized to make sure that the carbon dioxide stays within its legally bound storage site, where the carbon dioxide might be residing in a porous sandstone layer, so that if we send sound waves down as seismic reflection, the sound waves reflect on that different density of carbon dioxide and come to the surface, whereas if they reflect off the empty sandstone layer, then we have a different reflection. So we can determine exactly where the carbon dioxide is located at deep burial depth, even to the precision of just 150 million tons of carbon dioxide, which we now have injected 22 million tons. 150 tons is a really, really amazing sensitivity. These technologies can also survey in the shallow subsurface, of course, and that can detect groundwater by drilling boreholes, look at the salinity, look at the chemistry change of groundwater in case anything's leaking up from underground, and also look at the temperature and the pH and particularly the pressure in the groundwater to make sure there's no connection at all to those deeper pressures deep underground. So we have a very good ways of monitoring the underground, and that's getting better and better by the year. So here is a company which is effectively selling broadband, which you put broadband optic fibers down each of your boreholes, and those broadband fibers then communicate with each other using sonic and geophysical messaging, and we can determine the temperature of the rock, the pH of the rock, how stressed or strained the rock is. All sorts of valuable information can be produced in real time as it's happening. And also there's been a lot of technology developed by looking for remote controlled drones to survey the seabed, driving around on a grid pattern every day, looking for leaks of carbon dioxide, looking for pressure changes, looking for mineralogy changes or bacteria colony changes. So again, all these types of equipment are newly developing in response to the CO2 industry, but building on older equipment. So how long does carbon need to be stored underground? Here's one example where carbon is planted in a forest, maybe lasts for 60 years. Carbon planted in hedges maybe lasts for 100 years. Carbon buried in fields maybe lasts for 5 or 10 years. So this assemblage of carbon is very good for capturing carbon from the atmosphere with all that vegetation, but it's not very good at storing the carbon for long periods of time. Maybe those trees will last for 60 years, maybe the hedgerows will last for 100 years, and some of those hedges die. But that's understandable, that's allowable. We can understand the rates of this, we can understand where everything's located and know if something's going right or wrong. And that's really a short duration, a short cycle of carbon storage. But on the long cycle of carbon storage, then we have to go to a rock or a mineral. And so here's an example of both. Here's the White Cliffs of Dover, which are made of calcium carbonate, made of microscopic coccolith algae. And those microscopic carbonates are long duration mineral stores. Those White Cliffs of Dover may be 100 million years old compared with just 100 years for the vegetation on the left-hand screen. So which one of these is valuable as a carbon sink, as a long duration carbon store? Well, they both can be, but the mineral storage in long-term geology is the one I would favor for the long term. So for example, here is a graph where we're emitting carbon dioxide into the air, and the carbon dioxide increases very dramatically, but then it starts to dissolve in seawater. It starts to mineral rock weathering on land. It starts to weather and carbonate silicate rocks from basalt volcanic rocks, particularly magnesium carbonates are formed from that. And eventually the CO2 remaining in the atmosphere becomes less and less, but never quite gets down to zero. You need to go for multiple tens of thousands of years to restore the world back to zero, back to its pre-industrial state. And so that's why many people are keen on nature-based solutions where they can plant trees and grow vegetation. And that contrasts with geological storage, where you put one action in and maybe store a ton of carbon dioxide for a very long period of time. And that geological store doesn't change, it doesn't vary, it doesn't need much care and attention. So that stores very safe and securely for long periods of time with that geological storage. By contrast, if you use growing trees or growing vegetation as nature-based storage, then the trees grow very quickly and reduce the peak, and so do help reduce carbon dioxide. So the trees mop up the strong helper trees mop up the carbon dioxide, but don't last for very long. So if we want to store the carbon for a long period of time, we have to take the trees and maybe burn them and capture the carbon as a biomass carbon capture and storage operation, for example. So to combine two things together. And so because of these different durations of storage, it's very popular just now for many companies to sell offsets to say that if you pay £2, then you can be absolved of all guilt for the side effects of your holiday. And of course, most of these certificates of carbon storage, of carbon mitigation, are far too cheap. They're not real. They don't actually really store any carbon. They may decrease an emission somewhere, but that's nothing like the same as capturing and storing the carbon. So for example, here with verifiable good quality geological storage, we can justifiably claim the carbon will be stored for 10,000 years or longer. So we might sell one of those credits, those geological storage, genuine emplacement of CO2 underground. We might have that for £1. We could do other types of storage like enhanced weathering, of crushing up rocks, or of making charcoal, of planting trees, and then eventually of growing tomatoes or apples. But if we think about enhanced weathering, crushing up rocks, sprinkling it on the surface of a field, that gradually weathers away, where if enhance the rate of weathering by crushing the rock, but it still doesn't store carbon for very long periods of time. So again, you might store carbon for a 10-year period there. So that attracts less value, and you'd have to buy 10 of those credits to make up one geological credit. And the ultimate being carbon dioxide in greenhouses can help grow tomatoes or lettuces, or carbon dioxide can be put into fizzy beer. And that is only a transient short duration till the food's eaten or whatever. So that transient short duration is 1,000th of a year is what you're buying for one credit. So you might want to buy 1,000 credits to buy a 1 year of credit instead. So pay for what you want, be careful of what you're buying. Many things are too cheap. And going back to what we were talking about earlier on, then carbon dioxide storage is now really starting to happen. Around the UK, in the week of the 14th of June 2022, the UK government released the first commercial storage opportunities. So it released about a dozen different sites around the eastern side of the British Isles. And the idea is that companies bid for those, get the rights to that, develop the CO2 capture and transport pipelines, and could start storing carbon dioxide as early as 2027, once they've got the techniques and the technology out. Organized. So this could be the start of a multi-billion-pound carbon dioxide storage industry in Scotland, because in the east of Scotland, here in the North Sea, Scotland is extremely well endowed with carbon capture and transport and storage. And so understanding how that works is really important before you can start to identify the carbon capture and the carbon storage effects which you actually are having. So carbon dioxide capture, essential, very safe, lasts for long periods of time, can be stored very, very effectively underground, and can be detected and watched and carefully imaged as it does so, so that you will know in 5 or 10 years' time, you will now know where that geographer or that scientific study is located. So that's it. Thank you very much.
Okay, so we can see that we can securely store CO2. So what about capturing? I'll go through some examples. First of all, the conventional capture. This is the first example of large-scale CO2 capture in the world, 2014. This plant is, as it says on the building, SaskPower Boundary Dam, coal-fired power plant in Saskatchewan, Canada. And the flue gas is coming from over here, from not going up this chimney here, but coming through this enormous duct into a washing facility to take out the sulfur, and then into this facility here, which captures the CO2. It's captured in a liquid, which reacts with the CO2. Then after it's captured the CO2, the liquid's taken over to this tower here, where it's heated up, and the CO2 is then collected as the gas, which is then compressed in this building here, and then goes into a pipe, which is too small to see, and is taken away and injected underground, either into the sort of saline aquifer that Stuart was describing, so into sandstone, I think about 3 kilometres underground here, long way underground, or it goes into the local oil fields where it's also contained, but it is used to release more oil. Another project, the second one, is in Texas, in Houston. And this is the capture facility where the flue gas coming through this pipe here from this unit is reacted with the solvent to capture the CO2. This is the stripper where the CO2 is released. This is a plant to provide steam to drive it all, and the compressor is really too small to be seen. Again, this goes off through a pipeline and is used, in this case, all for enhanced oil recovery. This plant actually started in 2017, and it shut down in mid-2020. So there's some questions about when it will restart. It shut down when oil prices were very, very low or even negative in that part of the world. But it is interesting that it hasn't restarted yet. Another plant capturing CO2. This is capturing from hydrogen manufacture. The hydrogen manufacture was going on anyway. This unit here, a steam methane reformer. But the gas is captured in these units here. They use a different system. They use a sort of a solid, porous solid, which is sticky to CO2. The gas that's been used to make the hydrogen contains a mixture of hydrogen and carbon dioxide. It's passed through this sort of sticky, porous solid under pressure. The solid picks up the CO2. Then the gas flow is discontinued. It's passed on to one of the other vessels they've got. And it's the unit's depressurized, which is known as the vacuum swing absorption, and the CO2 is collected and pressurized again, in this case for injection into oil fields. A lot of these projects, early projects particularly, injected CO2 into oil fields because you could get some money for that. That was basically before the days when you could get funding for just stopping CO2 emissions. Another project, which is negative emissions, in this case, is capturing the carbon dioxide produced from fermentation to produce ethanol. So it's fermentation of maize in the American Midwest, in Illinois, to produce ethanol. You also produce carbon dioxide naturally from the fermentation. It's relatively pure, relatively easy to capture. And as you can see in this case, the goal, which is happening now, is collecting 1 million tons of CO2 per year and storing it in the saline aquifer. And as I say, that is CO2 that, because it's going through maize, was only very, very recently in the atmosphere. And now it's locked away deep underground. When you want to look at the net CO2 removal, yes, you have to look at other things in the overall process of producing that CO2. So you've got to think about energy used to make the fertilizers, the tractors, transporting the grain, any loss of soil carbon. But when you do all of those calculations with this huge net capture and removal, the process gives you overall a net removal of carbon from the atmosphere. A lot of these plants now in the US are being considered for CCS retrofit. So we could see quite a significant amount of CO2 capture, and as I say, genuine net removal of CO2 from the atmosphere. Another project a bit closer to us is at Breivik in the south of Norway. And this is now as a cement plant. As I said before, with cement, you get about 2/3 of the carbon dioxide that's produced comes from the limestone. It doesn't come from the fuel that's used to heat it up to make the cement. It comes from the limestone itself. It's still fossil though. and that all gets released to the atmosphere in cement plants. But in this one, they're collecting some of the off gases. You can only take about half of them through this pipe into the absorber tower, where again we use a liquid solvent to wash the CO2 out. The flue gases without the CO2 are then released through this extension stack here, going to the atmosphere. And then in this case, the CO2 is taken out. Looks like the stripper here, and it's turned into a liquid CO2. So it's a slight pressure, about something like 7 atmospheres, and refrigerated, minus 50 centigrade. Then it's taken over to this ship over here. And then the ship goes around the coast from south of Norway, partway up the west coast. It comes into this terminal here. The CO2 is transferred off into these tanks, and then it goes into a pipeline going offshore, where it's injected deep under the seabed. And this is the core of projects that the Norwegians call Northern Lights, also Longship, different parts of the project. And they're taking their own CO2, they're looking to capture CO2 from the cement works, and also from energy from waste plants. And they're also looking at shipping in CO2 from other parts of Europe. In fact, they're probably oversubscribed. So they're looking at taking CO2 from Sweden, also from other places in continental Europe. So this is due to happen very, very soon. First delivery scheduled by mid-2024. Very, very soon indeed. This is all real. So the UK is also looking to get CCS going by around the middle of the decade. And we're doing that through a number of clusters. The clusters are where we've traditionally had industry, so Central Belt in Scotland, Teesside, Humberside, Northwest, Mersey, the Wirral Peninsula, quite a lot in South Wales, and also there's some other industry, Southampton and Thames. Now the solid green circles have all got funding under a program called the Industrial Decarbonisation Challenge, which has funded studies of the clusters, the whole clusters, and also a lot of studies on individual projects. You can see the names of some of the storage projects that have been funded. There's about 41 separate capture projects, too many to show here, that have also been funded to get to a fairly advanced stage. Now, I'm showing 5 clusters there. 2 have been selected for track 1, that's Northwest, and a combination of Teesside and Humberside. There's pipelines coming out from both Teesside and Humberside going to a common store. Scotland is a reserve transport and storage cluster. And this summer we expect to hear which capture projects will connect to these clusters. And some of the capture projects can connect by shipping. So by the end of the summer, the pathway for UK carbon capture and storage is going to be quite a lot clearer. That'll be quite exciting. Now, most of what we're talking about there and so far is conventional, as I'll call it, CO2 capture and storage. But as we said at the start, quite a lot of the carbon dioxide comes from sources that you can't attach a big absorber to, sort of large units that we've seen, and you can't tie into a pipeline directly. So how do you get it? Well, the answer is you have to capture carbon dioxide from the air. And as Klaus Lackner, who's a pioneer in this area, said a few years ago, pointed out, obviously doing that, you can handle emissions from any and every source. It sets an upper limit on the cost of carbon management. It means that you can get to net zero. That's what we'll talk about later. It provides a solution to any risks of leakage from storage. You won't get very much leakage. from a whole collection of stores, you might get a few percent, but if you can't pull it back, it's still a lot of carbon dioxide. But if you can pull CO2 out of the air, it's just part of the overall economics. And because it's expected to be expensive, it encourages point source capture. It encourages people to do cheaper things if they want to. What it doesn't encourage is people saying, oh, well, I've done the best I can, I'm green, I've matched the numbers in some green taxonomy. Any further emissions I put to the atmosphere are just inevitable. You can't penalise me for them. The answer is, well, no, we won't penalise you for them. We'll just make you pay for them. Just pull them back out of the atmosphere. It's no big deal. Once we get the technology developed, and it will be developed soon, and when it is, it'll make a big change. So this is just showing some diagrams, if you like, for carbon dioxide removal. You've got BECCS, so you've got CO2 coming into the plants from the atmosphere, the plants going into a power plant or industry, getting burnt, the carbon dioxide going in the flue gases to a separator, examples that we've seen on those power plants, and then the CO2 either going to be used for something which would then be carbon neutral, but in realistic quantities going deep underground in storage in either aquifers or oil wells. Now we can do exactly the same separation or very similar separation from air. The CO2 concentration is low, but as we see, that isn't an insuperable barrier. And so you wash the CO2 out of the air one way or another, and then it goes to the same place. So this part of the CCS is conventional. This part's sort of conventional, but with a lower concentration of CO2. In all cases, you get exactly the same effect. CO2, carbon dioxide ends up underground, permanently stored. This is just a rather geeky diagram. The only thing you need to see is this is the energy that you're required to separate the CO2 in units of kilowatt hours per ton of CO2 separated. This is the concentration on a logarithmic scale. These are the flue gases. There's a range of concentrations. This is air, one concentration. And the energy to separate it is not much more than double. And this is fundamental thermodynamics. This is not what people observe. So basically, although it sounds like air, oh, it's got 1% of the concentration of a flue gas. Yeah, it has. But that doesn't mean that it's 100 times more difficult. It's only twice as difficult. So that's a fortunate finding, I suppose, but it's just basic thermodynamics. So what are people doing to capture CO2? Well, they're trying a lot of different things. It's an area of enormous development. It's actually an area that's been tremendously suppressed in development because, for example, as recently as about 2008, the Royal Society in the UK said, pulling CO2 out of the air that you put in there is geoengineering. It's not, it's picking up litter, but they said that. And people said geoengineering's wicked, we shouldn't be doing it. So carbon capture and storage is not, from air, direct air capture, has not received anything like the government support that it should have done for its strategic importance or compared to conventional CO2 capture. However, some pretty enterprising people, in this case started by David Keith, have looked at capturing CO2. This method washes CO2 out of the air with potassium hydroxide, which reacts to form potassium carbonate with the CO2. The potassium carbonate reacts with calcium hydroxide to make limestone, calcium carbonate, and then the calcium carbonate is heated up to about 800 centigrade, and it decomposes into calcium oxide and CO2. And this is a process that's been going on, I looked it up, it was about 5,000 years, ever since people have been making lime plaster for buildings. They've been using this calcination process. It's a very well-known process. Lime itself, once you make it, basically you can't help it picking up the CO2. This process accelerates it, but making calcium oxide, reacting it with CO2 to make calcium carbonate is what keeps our buildings standing up. You basically make something that you can turn into a paste, a lime mortar, cement, and then over time, the carbon dioxide in the air turns it into a rock. So this is accelerating this process. It's driving it through this modified cooling tower, reacting using a potassium hydroxide route. This process has been shown working at about a ton a day, 10 ton a day scale. It can be increased by having lots of contactors, lots of fans. And this is an example of a theoretical design for 100,000 ton a year scale. But right now in Texas, with funding from Occidental Oil, we have a very progressive chairman, Vicky Holub, really says basically Oxy is going to become a carbon disposal company. That's where our business lies in the long term, which is true, absolutely. Looking at designing this very large plant to capture 1 million tons a year. And once this sort of plant gets built, and you can see that just increasing the amount of direct air capture is a matter of money, then it really will change the dynamic of tackling climate change. Another very creditable example is Climeworks. They use a sticky solid, in this case, to capture CO2 from the air. Again, as the example with their products, they heat it up, draw a vacuum to get the CO2 released. You can get multiple units, put them together as actual examples to capture more CO2, but it tends to be at a much smaller scale. This is a unit being set up in Iceland, or that has been set up in Iceland. There, the CO2 can be mixed with geothermal fluid from one of their geothermal power plants and re-injected back underground where it makes solid carbonate. So this is the alternative CO2 storage method, geological storage method that I mentioned at the start. And this is capturing about, at the moment, about a ton a week, but they're looking at building a larger plant, 4,000 tons of CO2 per year. And this, I think, is operating as well right now, powered by geothermal heat, and as I say, using a geothermal field essentially to inject CO2. And then when the CO2 is underground, it's dissolved in water and it reacts very rapidly over a period of months with the volcanic rocks that are in that area. The volcanic rocks essentially have had CO2 cooked out of them really in the past. They're very reactive, very ready to grab onto CO2. It might happen over geological timescales as the rocks weather, but this process speeds it up, takes it out of the air. So just another reminder, another thing that people look to do with CDR, carbon dioxide removal, using direct air capture or biomass energy with carbon capture, is to make synthetic hydrocarbons, and that's fine. You can have a cycle which takes CO2 out of the air, reacts it with hydrogen made from electrolysis using renewable electricity to make liquid fuels, puts the liquid fuels, but you take the liquid fuels, burn them in a plane, sustainable aviation fuel. The CO2 goes in the atmosphere, you grab it back again, you've got a cycle there. You will get some losses, you will need to take a small amount of CO2 out of that cycle for storage. But you can perfectly validly, from a climate point of view, have another circuit where you take CO2 out of the air, you put it deep underground, and that CO2 allows you to take fossil fuel from deep underground, burn it, and put the CO2 in the air. I'm saying it's probably nice to achieve that removal before you extract the CO2 to make sure it's intrinsically linked with producing the CO2. And both of these routes give you liquid fuels, net zero emissions, net negative if you want it to be. And they can really, the choice between them is a matter of cost and a matter of availability of cheap electrolytic hydrogen. But both of them have to have carbon dioxide removal from the air at the core for net zero. So the UK is the first major economy to put net zero emissions into law, and it's actually net zero greenhouse gas emissions. So it's not just CO2, it's other greenhouse gases as well. And what the Act said was net zero means any emissions will be balanced by schemes to offset an equivalent amount of greenhouse gases from the atmosphere such as planting trees or using technology like carbon capture and storage. But I think when you look at it and think about actually what you need to do for the climate, you don't need to offset. Net zero means that you actually capture CO2 and put it away permanently. And if you want to put the net into net zero, you need to capture as much CO2 as you can at source. And if the alternative is taking the CO2 out of the air, you will capture 99% or more of the CO2 in a flue gas. And that may even get to the point where that's all the fossil carbon in that flue gas stream. Obviously, if it's capturing from biomass, you're getting a net removal. But even from fossil power plants, they're quite likely to get to net zero or very, very close just by conventional CO2 capture on the chimneys. You'll also need BECCS, biomass energy with CCS, and DACS, direct air capture with CCS, for capture of CO2, fossil CO2 via the atmosphere, and permanent storage. I think we've said enough about that, but it really is important for all other fossil CO2 emissions. And then you will also need, because we're worried about climate change, and other greenhouse gases give you some amount of the climate change effect we're seeing, methane in particular, you will also need additional BECCS and DACS to compensate for those greenhouse gas emissions. And that's compensation. You can work out the ratio, but it's easy to do. You will have to take CO2. You can't really capture methane from the atmosphere, but you can capture CO2. So finally, I'll leave you something that struck me at COP24 when I arrived at Katowice airport and was looking to change some money. I went down the entrance foyer and I came across this advert from the Global CCS Institute that basically says it all, I think, in terms of climate change. We must pursue carbon capture and storage like our lives depend on it, because they do. And I think, it's very unfortunate that we're in a position of having dangerous climate change to face. It's a terrible legacy to leave our descendants. But if we also leave them with proven ways of using fossil fuels with net zero greenhouse gas emissions, and also with ways of removing carbon dioxide from the atmosphere, because remember, we're going to have to do that in the second half of the century. And those ways are fully developed and proven, and it's just a matter of money. Well, that's, it's a mixed legacy, but it's not too bad. And that's certainly what the UK CCSRC and its members are hoping to do as their contribution to net zero, and indeed to net negative, and as a result, to successfully tackling climate change. Thank you.